Good day to my supervisor, other markers, as well as my fellow peers. Today, I will be discussing the effective removal of phosphate sulfate from water environment complex with copper alginate hydrogel beads. I know this topic sounds too heavy to get a grasp at, so let me make it simple by saying this entire research is done on the hope of removing toxic chemicals from effluent wastewater. To help you get settled into the rest of my presentation, I will be explaining the background of my work answering these four simple questions under the introduction. So how do these contaminants end up in water bodies? Starting with phosphate. Phosphate is an anion consisting of a phosphorus atom bonded to five other oxygen atoms. This compound is heavily present across the nature in the form of rocks and mineral deposits. The problem arises when the addition of excess man-release quantities. Salt and ester forms of this orthophosphoric acid are generally found in runoffs of agricultural lands, lawn fertilizers, as well as untreated sewage water. So they are orthophosphates. Boiler treated water detergent solutions are good examples for polyphosphates. Wastewater solids and certain type of bacteria are good examples for organically bound phosphates. So all these forms of phosphates, once introduced into water bodies, creates an excess phosphate concentration. Moving along to sulfate, it is an anion consisting of a sulfur atom bounded to other four oxygen atoms. So to mention, it is almost surprising to see the number of substances consisting this seemingly poisonous and harmful chemical that we use daily. It is found in shampoo, conditioner, face wash, toothpaste, and even in drinking water. So apart from the domestic releases, industries including oil refinery, pharmaceutical, and cleaning supplies all release sulfates into water bodies in bulk amounts. So arriving at the second question on what effects do they have in water complexes, it is very simple. We've been learning the introduction of phosphates can cause eutrophication and result in a decrease in dissolved oxygen level since grade school science. So sulfur, on the other hand, results in marine algae overgrowth as well as dissolved oxygen reduction in natural water bodies. So addressing the third question, I will be discussing what are hydrogel beads. So hydrogel is a 3D structure of a polymer with a porous structure that can be synthesized with one or more monomer with the ability to absorb water. Its water retention ability and cost effectiveness in preparation has led the modern day researchers to focus of its incorporation in wastewater treatment. So the final question on how do you incorporate it is very simple. Again, this research is completely based on addressing this problem. At the beginning of my research, I drew out an aim to help me keep on track for the entirety of this research. So that is to conduct experimental work on developing hydrogel beads and to conduct various testing on effectiveness, chemical properties, as well as physical properties. So this aim guided me to identify and be thorough enough for the research questions. Therefore, the questions are how to prepare alginate hydrogel beads and how to impregnate metals that effectively remove anions into these hydrogel beads. So moving past the introduction, let me help you brace yourself for the methodology by presenting some of the key knowledge areas under the literature review. So there are several existing methods for phosphate and sulfate removal in the world. So they can be divided into subsections as you can see: chemical, biological, and physical. Taking chemical into consideration, the most common practice is incorporating common chemical systems for salt sedimentation and coagulant precipitation. So as an example, I can say the use of lime or calcium hydroxide is a very common usage. So the most common physical methods are anion removal through magnetic field method, where you use activated magnetic field to isolate the anions, electric coagulation, which uses an electrode to accumulate the anions. So the biological methods include the use of certain identified or modified bacteria species just to remove the targeted anions. So the above discussed technologies all have the potential of removing sulfates and phosphate in good percentage values. So removing 75% of the above phosphate and sulfate is essential in the attempt to avoid water pollution globally. So according to Health and Safety Regulations Authority in US, the globally accepted concentrations for phosphate and sulfate in effluent wastewater stand at 0.05 milligram per liter and 500 milligram per liter respectively. The only exception is in running water bodies where the phosphate concentration is up to about 0.1 milligram per liter. And so this research focuses on the chemical removal method, precisely the absorptive methods done through hydrogel incorporation. So over the past few decades, several researchers developed many theories, suggested many chemical compositions, and even succeeded in many of the cases. But the first constraint I observed in the existing methodology surfaces with removing two different types of anions in the same batch utilizing the same method. Phosphate anion has a valency of 3, sulfate has a valency of 2. So far they are not very successful in approaching both together. The second constraint I observe is the effectiveness of anion removal. The percentages seem quite low. And as an example, I can say racine ion exchange has a 55% removal, and addition of coagulants about 61.4% removal. So as discussed previously, hydrogel beads are a polymer and can be synthesized using different types, and they can be defined according to the type of polymer, basis of source, polymeric composition, durability, structure, and many more. So these beads have been prepared using different types of biopolymers or polysaccharides. Cellulose, gum, pectin, chitosan, alginate, starch are very good examples. This research focuses on alginate, and it is obtained from seaweed, and it also forms a gel-like structure when it is cross-linked. So the powder is readily available, hence I won't be preparing it. According to many researchers, there are several tests that can be conducted to confirm its healthy microstructure. So the cross-section can be studied under electron microscopy, particle size under transmission electron microscopy, phase compositions using X-ray diffractometer, and functional group analysis using the Fourier transform infrared spectroscopy. So when it comes to the absorptive performance, it can be done by preparing the beads into different batches of concentration of phosphate sulfate, different concentration of hydrogel beads, retention time dependence, and changing the nature of the fluidity, that is running water or still water. The most important part, methodology of this research can be divided into four parts: preparation of copper alginate hydrogel beads, determination of its microstructure, and determination of its absorptive performance. And if time won't be a constraint, I would be doing the fourth step, that is the studies under regeneration and the reusability of these prepared hydrogel beads. So the current status of my research on the methodology is to prepare and optimize the copper alginate hydrogel beads, and the studies have shown that the beads can be integrated depending on its use as well as the targeted anions. So the skeletal methodology in its application is quite similar, and each research incorporates the same kind of preparation methods for the hydrogel beads, and mine would be modified like this. So the sodium alginate solution can be prepared thanks to the technological maturity in this area by purchasing the sodium alginate and dispersing it in 100 milliliters of deionized water, that is 1.5 grams, at 60 Celsius and 2 hours of continuous stirring. The stirring time is entirely dependent from research to research and the component to component. So that is solution A. And the solution B can be prepared by dissolving 16 grams of copper nitrate in 1000 milliliters of deionized water, and this solution A and B can be put in together and prepare the solution C. So this solution C then can be further continuously stirred for 3 hours and then stirred at 60 Celsius just to ensure the cross-linkings are complete. So the attempt to integrate the copper is done within this time period, and once the solution is brought into exact conditions as the requirement, it can be passed down a micro pipette tip of a peristaltic pump and dropped into a calcium chloride solution of 2 gram per liter concentration. This is to ensure the cross linkage. So after the beads are aged fine for about 12 hours in this solution, they can be passed through a hydrochloric acid solution of 0.2 mole per concentration, and 6 hours it will stay there, and once they are done, using deionized water you can fluctuate the pH until it reaches 7. And it is very important for me to highlight the project's significance as it is undergoing sustainable engineering solutions. The base of this research is around the beads forming biopolymers, that is biocompatible, biodegradable, renewable, and a cost-effective approach. And my future work is carried out in the winter semester followed by the semester 2, where I will be conducting more research and preparing the hydrogel beads in the laboratory itself. and doing the testing methods as well. So finally, I would like to share my sincerest gratitude to Dr. Basu for the constant guidance throughout the semester. And this would be all from my end. Thank you for your patience and time. Have a great day.